All right, this video is on gravity. When we think about gravity, we're going to think about Sir Isaac Newton. In the late 1600s, there was a bunch of scientists who were trying to figure out gravity and how the planets revolved around the sun. Sir Isaac Newton was not one of those scientists. He was off on a different tangent. But there was a guy named Edmund Halley who was very much trying to figure out planets. He was the guy who discovered Halley's Comet. And he was out to dinner with two other scientists. One was called Christopher Wren, who was most famous as an architect, although he did science on the side. Christopher Wren did all the big buildings in London. He did like St. Paul's Cathedral. He worked on a bunch of theaters. Anyway, all the big buildings in London are done by Christopher Wren. And they were out to dinner with another guy, Robert Hooke, who was the first guy to discover what a cell looked like. And they were trying to figure out the motion of the planets, and they couldn't figure it out. So Christopher Wren says, well, I'll give 50 shillings to whichever of you two can figure this out and explain it to me. And they couldn't. So Halley went to Sir Isaac Newton and said, like, can you help me with this math problem type of thing? And in response to that, Newton wrote his famous book, the Principia of Mathematics, which is all the laws of motion, and it's a great math book. He actually wrote it in 3 editions, and the Royal Society published the first 2 editions, but you really needed the 3rd edition for them to all make sense, and the Royal Society ran out of money because the year before they had published this horrible book called The History of Fishes, and surprisingly no one wanted to buy that. So the Royal Society went broke and they couldn't publish Sir Isaac Newton's last edition, the 3rd edition to his book. So Halley decided to front them the money and get that book published. And what I love about the story is the Royal Society then reimbursed Halley by sending him a bunch of copies of The History of Fishes, as if anyone ever wanted that. So that's the history on how Sir Isaac Newton published and described this whole thing and why that happened. And he really came up with a bunch of stuff was involved in his theory. Like he actually was able to figure out the mass of the Earth. And the inverse square law of gravity. So it was Newton that realized gravity did the moon and all the planets. All right. So there's this thing called the inverse square law. The farther something away something is, the weaker gravity gets by the square of that distance. It's not linear, it's squared. And so things that are very, very far away, gravity will get weaker and weaker and weaker. All right, so here you have the universal law of gravity, and this is what Newton published, which is the force that acts on it is equal to capital G, which is a gravitational constant, all right, and then the mass of your 2 objects, object A and the mass of object B. So if you're looking at the Earth and the Moon, you'd have the mass of the Earth and the mass of the Moon. If you're looking at 2, billiard balls on your pool table, then you would have the mass of each of those billiard balls. And that is all over the distance squared. And that was the key. They couldn't figure out that this elliptical orbit had the distance squared. Okay? So that's the universal law of gravity. That's the main equation we will be using in this unit. All right, so the universal gravity constant, G, is a really, really, really small number. And that makes sense because gravity is a very, 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 very weak force. In order it to have any effect, you have to have a very large body, like the Earth underneath us. We can feel the gravitational effect of Earth because it is so big. But when somebody sits next to me, I don't feel the gravitational pull between me and the person next to me because it is so small. But with a very large body, you can start to feel it. So it is 6.67 times 10 to the negative 11, meaning you have to move the decimal 11 times to the left. So it's a very weak force, very weak gravitational constant, very weak force. Okay, The Cavendish experiment, now this is another kind of crazy scientist called Cavendish. He was like some recluse that didn't like to talk to people. But he did this famous experiment where he was actually able to determine the gravitational constant, that very, very, very small 6.67 times 10 to the negative 11. And he actually did this in his home laboratory. He was rich and he was able to have a lab in his house, and he didn't like to talk to people, so he spent all his time there. And so what he did was he took these two balls, right, and he could ever so slightly get one to attract to the other. And I love this picture because it's completely wrong. The idea that you can have a human standing here and not screw up the experiment is ridiculous when you're talking about such a very precise experiment. Cavendish actually did this experiment, and he had to manipulate 17 different things remotely, but he did it from another room, and he used a telescope to look at the mirror, right? I mean, he actually used a telescope because his gravitational pull would have been enough if he walked into that room to screw up this experiment. But the very basic idea of this experiment is that if you have perfectly balanced rod, right, with two balls, you could get these two to attract and rotate and have this mirror ever so slightly rotate. But you can't do it standing there. You got to be somewhere very far away because the gravitational pull between these two balls is going to be really, really tiny. Okay, so just for fun, let's start to do some math. So if you have a mass of an object A, it's going to be, say, 1 kilogram. Then you need the mass of the Earth. By the way, Newton was able to mathematically come up with the mass of the Earth. Cavendish, using similar technique to finding G in the previous slide, was able to come up with the mass of the Earth within 1% of our current calculations. So you take the mass of the Earth, the mass of the object, and then you have to take the distance. And this is where people get a little messed up. The distance is the Earth's radius. When we do these calculations, we pretend that the Earth is one center point. So even if you're standing on the Earth, the distance there isn't 0. It's the distance of the Earth's radius because you're getting pulled towards the Earth. And when we do our calculation, make sure you remember to do the radius of the Earth. All right, so we have 1 kilogram on the surface of the Earth, and we take our gravitational constant here, which is the very small number, 6.67 times 10 to the negative 11. We multiply it by the 1 kilogram mass A, times the mass of the Earth, yes, a very large number, 6 times 10 to the 24 kilograms, and then the radius of the Earth, and then we square that. So yes, I want you to go get a calculator right now and make sure that this comes out to 9.8 newtons, which we said it should come out to 9.8 newtons because a long time ago when we first talked about force and mass and acceleration, we said 1 kilogram on the surface of the Earth equaled about 10 newtons. Remember that? It's really 9.8. Go right now. Yeah, seriously, go get a calculator because this is the exact problem if you're using your calculator wrong. And you're not putting in parentheses, or if you don't have a scientific calculator, and remember how I did that whole calculator thing at the beginning of the year, this is the exact problem where you're going to get messed up. Exactly here. So right now, no joke, go get your calculator and do this. Seriously, go get your calculator. Go try this. Okay, hit pause if you haven't done it yet. All right, let's keep doing our sample problems. So, using Newton's second law, remember this? Force equals mass times acceleration. You can rearrange for acceleration. We also get the 9.8 meters per second, so we just like consistency. Okay, here you go, the inverse square law. This is what was screwing everyone up way back when. Don't know why, but the inverse square law on the distance. And When we look at the circle, if you're on the surface of the Earth versus if you come out twice the Earth's radius, it then has 4 times the area. Okay, so that's why it's going to be the inverse square of something. We're going to go over this a little bit more. Another way to think about this, and this is a perspective thing, is, and if you don't like this, or this is in art too, the way things work, but at twice the distance, the face is going to be 1/4 the size of somebody who's up front. Okay, and no, you don't have to do this either, which is why it's all grayed out, but if you have a card that is 4 times the size of one card, you can cover it up by holding it at, I guess half the length is what I want to say here, but if you hold the big card at twice the distance, the small card will cover it up. All right, weightlessness. So weightlessness, certainly if you are in outer space, like really, really far from any object, you could experience weightlessness. But when you're in orbit, we think we experience weightlessness, but in actuality, the Earth's gravity is 90% of what it is here. It's 10% less. And so the question is then, why do people on the space shuttle think they're weightless? Earth's gravity is acting on them. And the answer is, it's because the shuttle is falling. It's falling back to Earth, and it's falling at a rate. So as what we call orbit, when we look at orbits, as the shuttle falls, it's just falling at a speed fast enough that the Earth curves under it. And so the astronauts are falling. They feel weightless, but there is actually gravity acting on them. We know there's gravity acting on them because if there wasn't, they would just go straight out into outer space. They don't. They curve around the Earth. It's funny the things you remember in life, but I remember in my high school physics class, one of the questions on the test was, if a knight in shining armor enters an elevator with you and you suddenly feel weightless, what do you do? And it was short answer, and I think I responded, you beat the crap out of the idiot who rode the horse into the elevator because he obviously broke the cable, and if you feel weightless, you are now, about to die. But this goes to the satellite that we just saw. And remember, you've seen this before, but if you're standing, you have normal weight. If the elevator's going up, you feel heavier. If it's going down, you feel slightly lighter. And if you're in free fall, you feel weightless, kind of like the people in orbit. Okay, I think this is a horrible drawing and an awful example because Ferris wheels do not go fast enough, in my experience, to throw you up and make you feel weightless. Where do you feel the lightest? I mean, I'm telling you, when I'm on a Ferris wheel, it's B that always scares me the most because I hate heights and I can't see anything. And the answer they want you to say is A because you're at the top and you're getting thrown up and, gravity's acting opposite. I think it's just a bad example, though. So instead of thinking of a Ferris wheel, think of a roller coaster that's going really, really fast. And then you can imagine feeling that. All right. Yeah. Ferris wheel. Okay, you can do it by just swinging something, a bucket or something. It feels lightest at the top. All right, NASA's Vomit Comet. Who wouldn't want to go on that? NASA has what they call a Vomit Comet, and it is just an airplane. It's a very padded airplane, though. And what they do is they fly this airplane up, and then they just let it go kind of into this dive, this free fall dive. And so when they're in free fall, when they're going down, everybody feels weightless, or they feel like throwing up.